Well, I hope everyone has enjoyed lunch and networking with colleagues. Let's return to our recognition of several of our peers for technical and literary excellence. Thank you. At this time, let me invite Achille Messac to the stage. Now, as you know, AIAA's Technical Excellence Awards have a prestigious reputation throughout the industry, and it's truly a pleasure to help recognize those who have made notable contributions. We're going to begin with the AIAA Aerospace Design Engineering Award, which recognizes design engineers who have made outstanding technical, educational, or creative achievements that exemplify the quality and elements of design engineering. The 2016 recipient is the Boeing Hypersonic Design MDAO team for their design of novel hypersonic vehicle concepts and development of the multidisciplinary analysis and optimization tools critical for success. Accepting the award is Kevin Bocut, who led the team. Please join us on stage. The AIAA Faculty Advisor Award recognizes the faculty advisor of a chartered AIAA student branch who has made outstanding contributions. The 2016 recipient is Amritur Anil Kumar, professor in the Department of Mechanical Engineering at Vanderbilt University. He's recognized for passionate promotion of novel aerospace design activities, community outreach, and mentoring of students to success at national competitions and pursuit of aerospace engineering careers. Dr. Anil Kumar, please join us up on stage. Now we continue with the AIAA Structures, Structural Dynamics, and Materials Award. This is presented for outstanding recent technical or scientific contributions in those disciplines. This year we recognize Tony Wass, who's the Boeing Egvet Endowed Chair and Chairperson of the William E. Boeing Department of Aeronautics and Astronautics at the University of Washington. He's being recognized for pioneering contributions to the development of innovative, experimentally validated computational models for progressive damage analysis of polymer and hot ceramic composite materials and structures. Tony, can you join us up here? Now let me invite Technical Director of the Engineering and Technology Management Group, Nancy Anderson, to the stage once again. The AIAA History Manuscript Award is presented for the best manuscript dealing with the impact of aeronautics or astronautics on society. Our 2016 recipient is Alexander McDonald, who is Program Executive for Emerging Space in the Office of the Chief Technologist at NASA headquarters. He's also in the Civil and Commercial Space Division of the Jet Propulsion Lab. His winning manuscript is The Long Space Age, an Economic Perspective on the History of American Space Exploration. Dr. McDonald, please join us up on stage. The AIAA Pendray Aerospace Literature Award is presented for relatively recent outstanding contributions to aeronautical and astronautical literature. Dr. David Schmidt, Professor Emeritus in the Department of Mechanical and Aerospace Engineering at the University of Colorado at Colorado Springs, is recognized for sustaining and influential contributions to aerospace literature in the area of aerospace vehicle dynamics and control, including the comprehensive textbook Modern Flight Dynamics. Dr. Schmidt, could you please join us up on stage? Go ahead and stay up there. This ends today's ceremony, but we're going to ask our group of awardees to return to the stage for a photo. So would you please do that? We'll take a quick photo. And while that photo is being taken, I'm going to turn the podium over to Dr. Jeanette Domber, Aerospace Design and Structures Technical Chair, who's going to introduce our keynote speaker.
Thank you, Mason. It is a great pleasure to introduce our distinguished speaker today. Dr. Michael Gazarek serves as the Vice President of Engineering for Ball Aerospace and Technology Corporation, following a 12-year career with NASA. He has over 25 years of experience in the design, development, and deployment of spaceflight systems. He has contributed to the development of technology with applications to NASA's exploration, space operations, and science missions. His most recent role was as the Associate Administrator for the Space Technology Mission Directorate at NASA headquarters, where he led NASA's rapid development and incorporation of transformative technologies that enable the agency's missions and addresses the nation's aerospace community's most difficult challenges. Prior to that, he has worked in industry and government, including at NASA Langley Research Center and at MIT Lincoln Labs. Gazarek earned his BS in electrical engineering from the University of Pittsburgh and his MS and PhD, both in electrical engineering, from the Georgia Institute of Technology. Dr. Gazarek has received numerous awards, including NASA's Outstanding Leadership Medal and a Silver Snoopy Award, one of NASA's highest honors. Please join me in welcoming Dr. Mike Gazarek.
Well, good afternoon, and I hope you had a chance to enjoy that wonderful lunch and to see all the incredible work and the awards that we saw today. What a great event. So hopefully after dinner, after lunch and after dessert, I just have a brief and short presentation to talk a little bit about Ball Aerospace and, more importantly, a little bit about what's going on in the field of large structures in space. And so just kind of a quick summary of what I see is kind of state of the art. It's not comprehensive by any means. And a little bit about some of the challenges that I think we as a community face. Hopefully you saw that we had a quick little introduction video that had some of the recent accomplishments in Ball Aerospace, and I'll talk a little bit about those as we go forward. So again, thanks. It's great to be here, and I understand some of the folks have to leave here at 1:30, so I understand it. I won't take offensive if people have to leave, and I know that we can get you out of here before 2 o'clock and the rest of the technical sessions begin. So a little bit about Ball Aerospace. In fact, we just had the conversation at Table 1, so I'm sorry, Table 1, you're going to kind of hear a repeat of what we just talked about in the last 15 minutes. It started in 1885, Ball Brothers, really in the idea of, actually was wooden cans for kerosene and paint. That led to kind of what's the iconic, famous Ball jar, mason jar that I know many of us have in our homes. Actually sold that part of the business, still license it, and really are a packaging company. Ball Corporation overall, 65 billion aluminum cans. And one of the things you learn, and I just joined a few months ago, is you quickly learn when you get a can of soda or other cold beverages, you go look at the can and see where it's made. And you quickly learn not to have any other thing other than Ball cans in your house. Certainly when you meet with John Hayes, our CEO, highly advised to take canned water, not bottled, into the meeting. But beyond that, how do we go from the jars part of this to the stars? So it was actually 1956, and one of the Ball brothers in beautiful Boulder, Colorado, in essence had kind of a chance encounter with some researchers from the University of Colorado that were trying to do some control experiments for sounding rockets. They were having trouble, and the Ball brother was also having trouble making a business work, and so that was the connection that was made, kind of a long-standing relationship between Ball and the University of Colorado Boulder in aerospace, and it really began since then. 60 years later, we're at Ball Aerospace, the longest running business unit of Ball Corporation, and that's where we are today. So this year, 2016, later in the year, we'll be celebrating our 60th year in aerospace. What do we do in aerospace? Maybe not as well-known name as some of the larger corporations I think that we all know. And it's a variety of business, about a $900 million revenue company, Ball Aerospace. And really kind of three facets for those who don't know. We're largely a remote sensing company, I would say is probably the easiest way to describe it, both for civil space, and I'll talk about that, a long heritage in civil space. Especially this year, and I'll talk about this in a minute, but 25-year anniversary of the Hubble telescope, and Ball did all the instruments on Hubble. The Ralph Imager, all those wonderful images that Alan CERN and the Pluto team, New Horizons team have been showing, all came from the Ball-built Imager. And on Mars, a lot of the discoveries on Mars, especially some of the recent ones, came from the HiRISE Imager, also from Ball. So, and in fact, it was interesting, Charles Alachi, as many of you know, the director of JPL, announced his retirement, and they have it's a wonderful video, by the way, that celebrates his career, if you have a chance to see it on YouTube. Really well done. But it's interesting, Ball is a prominent role in many of those missions, including Kepler and the discovery of exoplanets, Deep Impact, HiRISE, Pluto. So it's all across the board in civil space. We also have a large part of our business in defense and the IC community, which of course we won't say much here, but nonetheless, their sensing needs, platforms, instrumentation is a big part of the business. As well as in tactical, and all the majority of the communication and navigation antennas on tactical warfighters are all made at Ball Aerospace. It's a very unique and niche market for us in the RF field. And then finally, we also look at the data, the exploitation of that data, and how to turn it from bits and pixels into useful information. And so there's a large group out in Dayton, Ohio that does a lot of that interpretation. So it's really from the interpretation of the imagery and the information that it provides to the hardware that enables those pictures. That's in essence who we are at Ball. As part of that heritage, and really what I want to get into today a little bit, is in large structures in space. So a little bit about, again, not a comprehensive view, but maybe more of a snapshot of what I'm aware of across our community in terms of where we're at, especially in the optical world of large structures. So Ball has been at this, like I said, since the 60s, looking at large-scale observatories from ultraviolet and UV back in the solar observatory days, through Skylab and then through Hubble. Now significant work on the James Webb Space Telescope, which I'll highlight in a second. But above and beyond, what's next? And certainly we did a project Jeanette Domber led here. She's sitting here as well today with DARPA on Moray, which is a large-scale diffractive telescope concept that was pioneered here just a few years ago. So as we look in the future, and I know this very week down at the AMS conference, a number of, if you follow Jeff Faust or others and some of the news, a number of conferences on where are we heading for large telescopes, including James Webb, among others. And we can see, the obvious flow to a larger and larger scale. Do they have to be deployable? How do we fit into the rocket shroud? Do we build them in space? Are we finally going to move away from the point where we build them here, fit them into the rocket, and then deploy them in space? Are we going to build in space? And I'll talk a little bit about that here at the end of the talk. In addition to that, we can look at sparse apertures. Instead of a monolithic structure, can we control spacecraft well enough, right, to position them to form a large aperture? And that requires there's been many attempts at formation flying of satellites. Is that the next trend? So I'll talk a little bit about that as well, and how that we think, at least as we see it, how it fits in. Can't say enough about Hubble. I think we all know this observatory well. Ball built all 5 of the instruments that remain on Hubble. We built the star trackers. We built a lot of the repair tools that were used to service Hubble. It's been an incredible accomplishment. Hubble, in fact, Senator Barbara Mikulski was just at Goddard Space Flight Center this week. I know that was one of the things she highlighted and how it really has changed the world. 13,000 papers, a Nobel Peace Prize that's been awarded, and numerous inspirations across the community, looking further back in the universe than we ever have. And so kind of remains maybe, of course, as state-of-the-art, the best we have in terms of serviceable observatory, 2.4 meter observatory system that's serviced, I think, 5 times. And John Grunsfeld leading the way in many of those missions, and we had him out along with a number of the other folks like Frank Seppellini to celebrate 25 years of Hubble. And so Ball was involved early on in, I would say, the state-of-the-art in terms of serviceable observatories. If we look forward a little bit to the James Webb Space Telescope that's now being built and assembled at the NASA Goddard Space Flight Center, Ball was involved in that as early as well, and that represents now 6.5 meters is going to be the largest observatory deployed. I think the first deployable optical observatory that's deployed in space. And it was really like many of these projects, as we all know in aerospace, started a very long time ago. And so there really was a cocktail napkin sketch, perhaps at an AIAA conference, don't know where it was from actually, in the early 1990s of where the original concept was deployed. And of course, we know some of the main features of that. We'll see here in the next couple pictures of the segmented hexagonal mirrors, the ability of a sun shield, a tennis court size sun shield to protect the infrared radiation from hitting the telescope. Really incredible accomplishments, a real origami kind of design concept to fit into the rocket shroud. That's where it kind of all started, as many of the ideas do in conferences such as this, the innovative kind of creative minds where they flow. Fortunately, it takes 20 to 30 years to get them to fruition, something, of course, of this size. Where is James Webb today? Again, being assembled. I think we're up to, there's 18 of the hexagonal mirrors. I think there's 12 now that have been installed at the Goddard Space Flight Center. I know at the end of December we had about half, we had about 9 that were being assembled. Each actively controlled from a control standpoint at cryogenic temperatures. So this is wavefront control of each of the membranes, chosen material, silicon carbide and beryllium, right, for stiffness and control authority. The whole mirror has to fold up to fit into the Ariane 5 rocket shroud and then deployed, on orbit 1 million miles away from Earth. No servicing this one, unfortunately, at this time that we can envision. Some point, hopefully, the Lockheed Martin guys at Orion will get us there, in the future as budgets permit. In the end, though, the state-of-the-art in terms of observatories today, and the first one that's going to be deployed in space. And so the challenges here, of course, are in terms of the control systems and the sensing systems and the materials to manage the thermal vibration and the ability, of course, to successfully deploy it once it's in space. That kind of, in essence, represents state-of-the-art of where we are today and will be launched in 2018. As I saw from the meeting notes from AMS, again, on the JW meeting they had this week, on schedule, cost and schedule to remain on track for 2018. So to kind of summarize a little bit of state of the art and then talk a little bit about maybe what the future portends, I really copied and borrowed this chart from Dr. Bannock. It was in a recent paper for the U.S. Frontiers from the National Academies, which I thought kind of nicely characterized both the aperture and wavepoint precision, and then put on some of the key points as we know today, and where we look at JW, where do we look at Moray, which I'll talk about here in just a second, both looking at the dimensions of the precision of which you have to control, especially for optical telescopes, and of course the aperture diameter or size. And no surprise that as you move up that curve, right, the investment, the requirements, the testing involved, the verification involved increases significantly. So one of the challenges maybe to look at this chart is that how can we break this curve? How can we, what technologies or approaches can we take to get the large sizes that we need for future applications, yet keep the dollars to something that we can and the governments can afford? And so that's the next couple charts really talk a little bit about what we've seen from all companies all across our community of what I think is out there in terms of state of the art, at least the ones that we're aware of. Again, and it's not comprehensive, and I apologize if I missed some significant work that may be happening, from people right here in this room. If so, you can catch me afterwards and beat me up. One of the main efforts in this area, funded by DARPA in 2010, was something called Moray. Again, here, diffractive approach. So, as opposed to a reflective system, the use of diffractive membranes, which allows a larger structure to be built. And so the concept here was on the order of 20 meters. That could be, and has a variety of applications, from exoplanet discovery to perhaps optical communications. And it really represents kind of state of the art in terms of what could be built from a structural point of view. it is limited sometimes in bandwidth, but there are a number of applications where that still holds. And the ability, of course, is to get to those larger sizes, especially to something that can be deployed in space. Because of the thin membrane, there's advantages in the mass. Challenges remain, of course, in the control, especially in concepts where the membrane is a significant part away from the focal length of the detector. So the ability to control almost formation flying-like concepts is key in some of the key challenges that was demonstrated in the lab at Ball Aerospace. What else can we do? That's one approach, certainly diffractive membranes and the ability to deploy telescopes. But what else can we do? And one of my favorite handwritten notes of all time from Warner von Braun, and I don't know if you can read it, but it talks about manufacturing in aerospace in the 50s when they were building the Saturn rocket. And it basically says, after many years of study of rocketry, I've concluded that welding is the most critical aspect. And that still remains true today, right? I mean, our ability in the end to manufacture, whether it be in space or on the ground as we do today, the critical aspects of welding, joining, machining, assembly, deploying, all still remain true today. That hasn't changed. So these next couple points talk about what it would be like to manufacture in space and the studies and so forth that are underway and kind of where some of the efforts that are underway today. If we look at maybe assembly in space, one obvious place to start with in terms of state-of-the-art is the International Space Station, certainly the largest structure ever built by man in space, now human-operated for how many years? 15? 15, right, 15 years. Amazing, amazing structure. Now, it did take a number of spacewalks, of course, to put it together, right? And over 100 and some launches, of course, to assemble it in space. But it does represent, I think, state-of-the-art in terms of large-scale structures in space. So above and beyond this, what could we do above that? What else could we manufacture in space? And you'll see there's some techniques now that's being considered that talks about the ability to manufacture components and structures in space. Clearly not as mature as the International Space Station, but they do, I think, represent the future of where we're headed. Let's start with two, maybe on a less grander scale. One is there's a concept that JPL was working with NASA and the Johnson Space Flight Center on the ability to deploy an optics in space off the International Space Station that I don't think has got funded yet, but we certainly, when I was at NASA, looked at it pretty hard. Optics, I think, was the acronym that we were using, to look at a robotically deployed optical telescope, I think on the order of 1.5 meters in space. So that was a concept underway. Also, structures, deployable large-scale structures in space that did come to TRL-6 are in the area of solar electric propulsion. And if you know that story, the ability to get to 50 kilowatt type electric propulsion systems in space, it turns out that the challenge is not in the propulsion necessarily or the power, it's in how do you deploy an array of that size in space. It really does become a structural and thermal challenge. And so the Space Tech organization, at least when I was there, had funded two efforts, one by ATK and another by a small company called DSS out in Goleta, California, that looked at both a 10-meter diameter, that's what's shown there up at the Glenn Research Center, development and deployment of a solar array. And in the bottom is a rollout technology. Some of that early work was done by DARPA, then picked up by NASA, and DSS now is working at today. Both of those got to deployable conditions on the ground at about TRL-5, some elements even up to 6. One of the challenges we know in this area is our ability to test on the ground. How do you test something, especially if it's going to be deployed in space? You need large-scale structures, and the gravity offloading is significant. It really becomes an engineering feat on its own, is the ability to deploy that kind of structure on the ground to counter the effects of gravity. So how do you test as you fly? It's a very difficult thing to do. Certainly what we're going to see, I think, in some of the challenges, our ability to model and trust our simulations and modeling to allow us to test probably subscale. That seems to be, the way that we're going to have to go. So that's 10 meters and about 50 feet rollout kind of represents, as far as I know, state-of-the-art in solar array deployment, some of the larger structures that are being considered. I think the Space Tech organization now at NASA is looking at funding these for a demonstration, perhaps off the International Space Station for large-scale arrays. The International Space Station, of course, does have arrays today that are very large in size. Again, a lot of those were used EVAs and spacewalks to help them deploy. Another concept, of course, is our ability to manufacturing in space, 3D printing, if you will, in space. And there's a company made in space out of San Francisco that has put a 3D printer on station and now has printed tools and devices on the International Space Station. And NASA, along with them, is looking at a roadmap of that to put a whole facility. And the idea here is kind of the Apollo 13 idea about ability to print parts as you need them, or filter boxes as you need them, circles and squares. You could print what you need, on orbit. If you take that even further, then you can imagine printing large-scale structures in space, and perhaps even printing optical structures in space. And there's even a concept and studies underway to look at printing entire spacecraft. I know there was a plan, at least when I was at NASA, to show the first demonstrated ability to print, send up just the raw elements and print and build the first CubeSat in space. And kind of revolutionary and different thinking. We turned to the national academies. In fact, Mason Peck was a sponsor of this study, to look at the academies, to look at some of the trends and some of the hype actually in our ability to look and manufacture in space. And so I know that report is out there and really shows some of the challenges and kind of has a roadmap involved in what it's like to manufacture in space. Other concepts, maybe slightly different than the printing idea, come from a company called Tethers Unlimited up in Washington State. I know there were a number of NIAC winners. Robert Hoyt had won a number of NIAC award winners when I was at NASA. That's how I'm familiar with this work, and so I just took this from some of their recent material. Really incredible to me ideas, and the idea that shown there, state-of-the-art, here's an observatory like Hubble that was launched off the space station. That's what could fit. Could you imagine a significantly larger structure that could be built in space? And if so, how would you do it? Robert and his team's idea is a trusselator, kind of build the trusses that then build themselves with a little spider kind of operation that uses composite materials in order to extrude and be able to build the structure in place in space. Again, low TRL nonetheless, and they have demonstration on the ground here with the, you can tell they're in Seattle with the 12th man, I think is what that represents. But nonetheless, they got a number of multiple feet of ability to produce and replicate itself in terms of trusses. So that's kind of where it stands in terms of TRL, but you could imagine the ability then to take those kinds of structures and make them in space. So if we kind of last chart here, then kind of those are some of the state-of-the-art applications. What are some of the challenges then that we face in this whole field? For some of the applications, it's optical. Large scale, as we talked about, are large scale deployable optical systems, perhaps sparse aperture, perhaps ones that are deployed. But that all involves in wavefront control, the ability to sense very fine distances and maintain wavefront type precision. The other kind of application is in multiple spacecraft instruments, i.e. like GRACE or MMS, and the ability to make a measurement that requires precise precision between spacecraft. So what are those are the applications, I think, as we see them today. And they also involve large structures such as antennas, especially for collection devices in the microwave and radio. And I think that we'll see advances in the RF first, like we do in many cases, since the precision there is not quite as required as we do for optical. What are the challenges? Well, one, as we talked about, is our ability to test as we fly, our ability to model, our ability to do the gravity offloading, and can we get more creative in that testing environment? The second one, of course, is in materials, and that's kind of obvious, but certainly in the new types of materials, it's not only the new materials, but our ability to understand them. The materials genome effort that's underway, for example, by the Office of Science and Technology Policy, really been championing the idea to make materials and, of course, understand them and digitally construct the types of properties that we want in them, and can we space qualify them, right? Can we take that material and really trust it in our designs? And could it have variable stiffness? There are some cases where could you tune the stiffness of a particular structure where you want it stiff when you're doing your operations, but then flexible perhaps when you're making a maneuver? And could you be able to tune it when you're looking at these large-scale structures and large-scale distances? Can we look at ultra-stable structures and new types of materials, right, that have incredible stability properties that we can rely on for these kinds of measurements? The other part revolves computation and sensing. The ability, and JW is certainly part of this, of putting an actuator on each of the segments and the ability to control each surface in 6 dimensions. That requires computational capability on board. And the next thing it requires is the ability to sense, especially either at long distances and or very precisely, picometer accuracy. And so one of the things shown on the bottom that we're looking at Ball, among others, with the University of Colorado and NIST, which is up in Boulder as well, is the use of optical cones. The idea of multi-tooth laser frequencies for a heterodyne type system that can then be sent out and use all those pulses in the heterodyne system then to make a very fine measurement to get you picometer accuracy. Right now, laboratory work only, large systems that are not ready to fly, but we are getting types of single meter type picometer distances. I know JPL is also doing this work, I think more on the RF side, I think as a follow-on to some of their GRACE spacecraft control. But this to us represents one of the big challenges as we move forward to look at these large structures sensing, control, new materials, and our ability to model and simulate what we're about to fly. So that's really a quick summary that I had today as we see large structures at aerospace at Ball. And hopefully you found that somewhat entertaining. And with this, I'll turn it back over to Mason, and I'll be glad to take questions later on, after the event. Thank you for your time and your attention. Thanks, Mason.
Stay up here for a second, okay?
Okay, sure.
Well, thanks so much, Mike. We appreciate your time here today, and as a token of appreciation from AIAA, we want to give you a gift.
Thank you very
Represent
much.
your terrific talk here, so thank you very much.
Thank you, Mason.
Well, that's it. Afternoon sessions will be starting in a little while, so we hope you enjoy the remainder of the forum. Thanks very much for joining us today.